Right. And so a graph is said to be continuous if there's no breaks or holes in the graph. So you're saying that you could graph the whole thing without ever picking up your pencil. Really, the definition of continuity is much longer, and when you get to higher level math, they'll give you a better definition. But so for right now, just think that you can graph the whole thing without ever picking up your pencil, then it would be continuous. So the types of discontinuity that we're going to talk about in this class is we have a first one here. It's called an infinite point discontinuity, and that's because these are going to asymptotes. So it's going to infinity and negative infinity, so we call that infinite point of discontinuity. You could have one right here where it jumps. So I can literally either jump your pencil to get to it. So that's what we call a jump. And a hole is that we've removed one point. So this is also could be called a removable point. So if it's removable, it's because there was one little hole there and we would just fill in the hole. So let's look at a couple of different types. So right here, I go from this point, I had to pick up my pen to go all the way down here. So this would be called a jump. Discontinuity at -5. This one right here doesn't have any of them. So it doesn't have an asymptote and it doesn't jump and there's no hole. So this one's actually continuous on its domain. And then this one right here has an asymptote at the 1. So it would be an infinite point of discontinuity. And we're saying as x moves towards positive or negative infinity, what happens at the end. So like as this one moves to the right, your end behavior going down to negative infinity. And as you move to the left, that's this one right here, your graph's going up to positive infinity. So it's just asking you, what does your graph do as you go to the left and the right of each of these? So let's see here. So the end behavior on these graphs here. So this one here is my x goes to the right. The graph is going up to positive infinity. And as you go to the left, it's also going up to positive infinity. So both of those would be positive infinity for them. So this one here, similarly, as you go to the right, it's going down, left, it's going down. So both of these are going to negative infinity. This one, as I go to the right, goes to positive, and this one is going to negative. So you'd say, right, you're going positive, left, you're going negative infinity. So you could also have it actually approaching a number, and that's what we call a horizontal asymptote. You guys probably learned with your rational functions last year. So if you look at this graph here, as you go to the right and to the left, it looks like it's actually approaching a line. So we're saying as you go to the left, it approaches -1, and if you go to the right, it approaches -1. It does not have to approach the same number on both sides. One of them can go to -1, one of them can go up to 4, depending on what your graph looks like. So let's look at a few here. So see this right here looks like it's approaching the, was that 1, 2, 3, the -2 line in each of those directions. So that's approaching -2 as you go to the right and to the left. The middle doesn't matter. It only matters what's going to the right and to the left there. So this one, as you go to the right and the left, it looks like both times it's approaching 0. That's what we have here. It's approaching 0. And this one, as we go to the right, it's approaching your line down here of -5. But as you go to the right, to the left, it's going to infinity. So you don't have to approach a number. That's an example of where you don't have to actually approach a number.